So this is my show and tell introduction, and what I've actually done is tried and shown the relationship between induction and recursion, and focused a little bit on recursive algorithms which are not of divide and conquer type, because I feel like we've gone into the divide and conquer algorithms in a fair bit of detail in this iBook. Um, However, that being said, I'll just quickly go through the binary algorithm. So binary search obviously is divide and conquer 101. We start with a list, numbers 1 through 9. What we're looking for is the number 10 in the list 1 through 9. As we can see, the number 10 is not in this list. What divide and conquer will do is find the midpoint, so element number 5, compare the element 10 to 5. We know that 10 is greater than 5, so we split the set 6, 7, 8, 9, find the midpoint, number 8, compare 8 and 10, so we know 8 is less than 10, get false, move on, split the list, what we've left with will be 9, compare 9 and 10, we know again that 9 is less than 10, we'll be left with no other items in the list, which means that 10 is not in the list and returns the index minus 1. Now that was on an ordered list or an ordered set. An ordered set is a set where there is a superiority relation between every single item or element in that set. So what that simply means is that if you have two elements A and B, A either has to be less than B, A has to be greater than B, or A has to be equal to B. It has to be one of these three, and this relationship is defined for every element in the set. On an unordered set, obviously there is no such definition. Um, so there are no binding properties as such, and we have a set here which is not in ascending order as we had before. We try doing binary search on this. Now if we do try doing binary search on this, let's say we start with the midpoint 9. We have no reference. We have no idea. So we do know that 10 is greater than 9. But we don't know if the numbers on the right hand side are all greater than 9 and the numbers on the left hand side are less than 9. So we can't divide. What we have to do is go through every single element in this list, compare it with 10, and then determine that 10 is not in this list. I'm just gonna draw these as trees. So this is the ordered list before. This is drawn as a binary tree. As we can see in this binary tree, the left child is always less than root. Let's call it the parent. Let's say left less than parent less than equal to, and the right child has to be greater than the parent. It's fairly simple. Let's try finding 10 again. I compare 10 with 5. I know, just change the color here. I compare 10 with 5. I know 10 is greater than 5, so I go right. Compare 10 with 7. I know 10 is greater than 7. I go right. Compare 10 with 8. Go right. Compare 10 with 9. And then finally return minus 1. Obviously, this is of order log n. Um, as the list is divided or cut by half at every recursive call. So we don't have to deal essentially with half the elements, or we discard half the elements at every single stage. So what you do have here is log 2 log n to the base 2. On the other hand, on the right hand side, we've got the unordered list. And I'm just gonna go through this example here of this subtree where left is less than the parent, the right is less than the parent, and left, sorry, the right is less than the left. So it's sort of violating all the rules of the binary search tree, which is here. Let's write that down. Right, so there is no way for us to sort of determine on which side would we get the number 10 if the number 10 were to exist in this tree. Um, so what we can do, and this would obviously be order n as we would have to go through every single element. The question now falls on how do we go through every single element in this tree. So here's a file tree. What we had before were numbers. Um, let's just replace that with files. There's no vertex missing here. So let's just replace that with 5. What we have is folders at level 1. So each vertex, so each vertex is either a file or a folder. Right. So the question is, I want to find the file abc.txt in this. Let's, for argument's sake, assume this node here, actually mark it in green. So this node here is where we have abc.txt. How do I then have a strategy to go and find abc.txt in this entire tree? What I can do is something called depth first traversal. That's what I'm going to go over here right now. So we go to depth first. The idea with depth first traversal is that you go through all the children, go through children first. So I'll go through all the subfolders of, so let's say I started the root, I started number 1. What I intend to do when I go left is to go through all subfolders of 1, the 1 left subfolders before I move on to the right hand side. So I'll check this. This is where I go next. Again, I go left first, number 3, number 4, and then I go back up. At this level, at number 2, I'm going to circle this in red, I've gone through the left hand tree of vertex 2, but I have not gone through the right. So I need to go through all subfolders of folder number 2. So I go right, check this out, check it for the file, so 5, go back up to the root. I've already seen the root. Go back down. 6, 7, 8, and 9. At this point, I finally reach or find abc.txt and will return the file. I'm going to do the same thing. This time, however, we go breadth first. My presentation actually focuses mainly on depth first, but I'm just going to go through this to sort of contrast the two approaches. I'm going to be super quick with this, and you guys can always come back to me with any questions if you have any. So we've got the root directory at level 1. Let's go to K0, got level 2, let's just call this 1, got 2, got 3. As in the previous case, we'll let abc.txt be in the rightmost child, or the rightmost leaf of this binary tree. What I do now is quite interesting. So the goal here is to go through every folder at a level before searching the subfolders. So I need to go through the folder, all the folders at the root level, all the folders at level 1, level 2, and level 3 in that order. Just going to take this. So I started the root, number 1, go left, 2, 3, 4, 5, 6, 7, all the way across to the next level, start from the beginning, 8, all the way to the last level, 9. At this point, I will be able to return the location of ABC. Right. Obviously, we're not limited to file structures or folder structures, which have, where a folder can only have 2 subfolders or only 2 elements or 2 children. We can have potentially an infinite number of subfolders within a folder. There are no restrictions. The only restriction, however, is, so each vertex can either be a folder or a file. The only restriction, however, is a file cannot have children, which is the same as the file cannot be a leaf. Sorry, that a file, I'm so sorry, that a file must be a leaf. So this is the sort of generic version of the file structure or the folder structure that we do have in our. Right. Just to go over the depth first search algorithm here. This is sort of the pseudocode in words. So I'll just go through it and I'll use colors as appropriate. So as you can see, you started each vertex. We started vertex number 1. Check if, again, actually I'll just say abc.txt. We put abc.txt again in the last or the rightmost child. the tree. Um, right, and then you check at number one, we start with the root, we check whether the item is in the vertex. If yes, we return the item. In this case, it's not in the vertex. We set the vertex as visited. So I've already checked the contents of this vertex, so I don't need to do it again. It's fairly straightforward. And then for each child, so I'll start with the left child in red. For each child that has not been visited, I will recursively call depth first search. So now I'm looking at this left subtree. As we did in the previous call, we start with this vertex, check if the item is in vertex number 2. The item is not in vertex number 2, we know this. We set the vertex as discovered, it's colored in orange. And then we move to each child. So I go left again. I'm just going to change color here and mark this in yellow. I go left, and now I'm looking at this subtree which consists of vertex number 3 and 4. Do the same thing, check if the item's in 3, it's not in 3, and I go to 4. Sorry about that. I go down to 4. At this point, at vertex 4, I have my stopping case. I'm just going to mark this in purple. No children. So I will return, I will go back up from here, go back up from here, and reach vertex number 2 again. Now I have to look at, so I have to go right at vertex number 2. So I look at this right subtree. I marked it in orange, and just take another color. Right. So I'm looking at this right subtree of vertex 2. This is the left subtree of vertex 2. So I look at the right subtree of vertex 2, check for the file. The file is not in this vertex, which is number 5. I go back up, go back to the root, and then follow the same procedure for number 6. Go down to the left to 7, go back up, 8, and 9. Finally, when I do reach vertex number 9, I do find this condition to be true. The item is in the vertex, so I will return it. So I return this item back. The one thing to note here for anyone who did data structures in the last semester previously, this approach to traversing the tree, or by traversing I mean we go through every single vertex in the tree. This approach is called in-order traversal. And what I mean by in-order tree traversal is that you check the root first, you check the left child after the root, and then you finally check the right child. So that's the order for in-order traversal. And this is sort of depth. Here's just a quick snippet of the pseudocode. It's good old Wikipedia. And I've just attached a separate PDF of this presentation with the video so everyone can have a look at it. if you have any questions, you can always come back and I'll be really happy to answer them. Right. Moving on quickly now. So this is induction versus recursion. The idea with induction is that you start with the basis. So the basis is that this the deepest subfolder, sub K, is part of a folder called J. J is a part of a folder called I. I is the part of the root directory. We know the file for, or let's say that what we need to prove is that the exact location of a file is somewhere in this chain. The base case is to sort of say the exact location of the file. So if I were to write this down here, let's say the file is in folder sub K. It could look something like C documents. Let's call it discrete math module for abc.txt. That's Q0. So you know the files here. The inductive hypothesis is that the file is in for any arbitrary k, the file is in subfolder k. If the file is in subfolder k, and that's our inductive step which comes, if the file is in subfolder k, it must be in subfolder k plus 1. Sub k plus 1 is basically a folder, or you can call it a superset, which is a folder that consists of sub k and a bunch of other folders. Sub k plus 1 could also just consist sub k and nothing else, but k plus 1 must at least contain sub k. Subfolder k. So here's a small proof. So we let S be a file. I'll just use some colors here for, I don't know if it helps. I hope it helps. So S is a file and capital S sub K is a folder where K is the depth of the folder and I is the instance of the folder. So if I were to quickly draw this, you have S1. So this is S0, which is the big folder. You have S1, S11, S12, S13. So this is level 1. And in level 2 you have S21, S22, and so on. Here you have S21, S22. I'm sorry about the notation, it's a bit jumbled up. Right, so the idea is that the indices, as you can see, the folder structure is pretty well defined, where one is a set of another, subset of another, I'd say. So moving on, right, so here's our theorem that if there's a folder S of k, and if S of k is a subset of S of k plus I for all I which is greater than 0, so for all folders that are either S of k, S of k plus 1, so this can be k, sk plus 1, sk plus 2, sk plus 3, and so on. if the element s, and let's s equals abc.txt, if we continue with our old example, if abc.txt is in s of k, then it must be in the folder which is s of k plus I, where s of k plus I is a superset, or is the parent directory. So we've got the basis step and we've got the inductive step. The basis step is pretty simple: check whether the file is in the address where it's supposed to be, and the inductive step is telling you that any set sk plus 1 can be expressed as a union, can be expressed as the union of its subsets. The union of the subsets can be, and this is where we put our inductive hypothesis in. S of k, S of k is a subset of S of k plus 1. So we've got S of k, which is a subset of S of k plus 1, and S of k complement, which is all the elements that are in k plus 1 but not in S of k. And I guess the rest follows. So we can see that S of k has S of k plus 1 here contains S of k. And if S of k contains the file, then S of k plus 1 thereby contains the file, and so on. Just coming to the last couple of slides. Sorry, this has been a bit long. So what induction essentially does is we go from inside to outside. So we start with the file Q0, which is the basis, go to Q1, Q2, and then end at the root Q3, where we can say that the file abc.txt is in the root directory Q3. So that's induction. Recursion, on the other hand, does the entire process in reverse. So we actually start at the root, that's Q0, let's call this R0. That's the first time the recursive function is called. We drill down into the subdirectory R1, go to sub2, 2, R3, and then finally reach something called a stopping case, where there's one of two outcomes. You either find target or return empty-handed. So that's the difference between, I guess, induction and recursion, where one is the complement of the other. And finally, the maze puzzle. So depth first search is actually used for this, where the maze is a graph. The maze has, so the objective is obviously to go from the start to the finish. If we do recursion, we start at the finish line and we go back. So to find start, each vertex has a left, right, or center child. So what we do is we can use something like depth first search, and let's say we go right. So we go right, and then we reach this, we go right, reach here, we go right, reach a dead end, come back, go center, go right, reach a dead end, take center, go right, dead end, center, go right, again, go right. Now this leads us back here, which is connected to another part, so this is not a tree. So vertices can come back and connect with each other. Um, so going on, go right, so like that, goes right, right again, go right, hit a dead end, center, center, go right, dead end, center, dead end, left. And that's how we reach the start. So that's depth first. Um, I'm sorry this presentation was a bit long, about 30 minutes now. Do let me know what you guys think, and again, I'm sorry for how long it is.